Hello my dear students. So in my last class I started explaining about electronic spectra of transition metal complexes. So we had a brief introduction about what is meant by electronic spectra or electronic transition. So that is the promotion of electrons from an orbitals of lower energy to an orbital of higher energy due to the absorption of electromagnetic radiation, which results in a change in the arrangement of the electrons in the orbitals of the molecule is termed as electronic transition. And we also saw that each electronic transition causes an absorption band in the electronic spectrum of the molecular species. And further we saw what is meant by LS coupling or Russell-Saunders coupling and the possible interactions, that is electronic interactions which can be formed. So like 3 possible interactions was studied, that is spin-spin coupling, orbit-orbit coupling and spin-orbit coupling. So I explained about spin-spin coupling and also orbit-orbit coupling, and in this session we are supposed to discuss about spin-orbit coupling. So in which coupling of spin and orbital angular momentum of the same electrons occurs. Okay, so the coupling between the spin of one electron with the orbital angular momentum of a different electron is negligible and hence ignored. Okay, so this is what we studied in our last class, and also while studying the spin-spin coupling we took the example for D2 electrons, that is example of titanium, zirconium and hafnium. So where we saw there will be the 2 electrons in the outermost shell of these elements, so that is group 4 elements. For D2 electrons, so if we see the group 4 elements, so there we can see the electronic configuration at the outermost shell of these elements will have 2d electrons. And we saw how the spin-spin coupling is going to occur in this, and orbit-orbit coupling describes about the total angular momentum quantum number for 2 electrons, which is obtained by adding vectorially orbital angular momentum. Okay, so this is where we stopped in our previous class. To be more precise with the introduction part of Russell-Saunders coupling or LS coupling, so let me give a brief introduction about the scientists of Russell and F.A. Saunders. So in atomic spectroscopy, that especially in atomic spectroscopy, so the Russell-Saunders coupling, which is also known as LS coupling, specifies a coupling scheme of electronic spin and orbital angular momentum. Okay. So this was first studied, the coupling scheme was first studied by H.N. Russell and F.A. Saunders in the year 1925. Okay. So therefore this coupling scheme named after these 2 scientists. Okay. And we also saw that for heavier atoms, that is if the atomic number is more than 30, so for such type we are going to use another term, that is JJ coupling, which gives a better approximation for atomic wave function. Okay. So to understand this spin-spin coupling and also the orbit-orbit coupling in a better way, we should be familiar with the structure of the atom. Okay, as we all know, the structure of the atom is so it consists of a nucleus. Okay, so nucleus is the centermost part of the atom, and electrons will have a definite angular momentum. That means, so we know that electrons always revolve around the nucleus. Okay, so when they revolve around the nucleus, so these electrons will have a definite angular momentum. That means in a particular angle, so the movement or the rotation of the electrons will be taking place, and that is why it is called as orbital angular momentum. That means, so the electron which revolve around the nucleus in a particular direction, it will possess a orbital angular momentum. In the same way, the electron itself will have a spin. Okay, so it will have a spin, and that spin which has been possessed by the electron, so that is what is called as spin angular momentum. Okay, so both orbital angular momentum and spin angular momentum is going to be possessed by each electron which is revolving around the nucleus in a atom. Okay, so this is how we are going to understand the structure of the atom. Okay, so now suppose if there are more than one electron, what happens? So if there are more than one electrons, so definitely we will have more orbital angular momentum and more spin angular momentum which has been possessed by each electron which is going to revolve around the nucleus. Okay. Then what happens? The condition will become very complex. Suppose if there is only one electron is present, then we can calculate what is the orbital angular momentum which has been possessed by that particular electron, and what is the spin angular momentum which has been possessed by that particular electron. That can be easily calculated, whereas if there are more than one electron, so then it is difficult for us to calculate the values of L and S. Okay. So L is the symbol which represents the orbital angular momentum, and S is the symbol which represents the spin angular momentum. Okay. So when the condition becomes very complex, and there will be the coupling of orbital and spin angular momentum, and this is why we are going to call this coupling as LS coupling. That means L means orbital angular momentum and S is the spin angular momentum. So here we are going to see the coupling of orbital angular momentum and spin angular momentum, that is why the name LS coupling. Okay. So so this is how, by looking at the structure of the atoms, we are going to understand about spin-spin coupling and orbit-orbit coupling. Okay. So moving on to the next topic, that is spin-orbit coupling. So the total angular momentum for a system of electrons denoted by J is obtained by coupling the resultant spin S and resultant total angular momentum. Okay. So now you have to understand what is meant by L and what is S and what is J here. Okay. So L is the total orbital angular momentum, S is the total spin angular momentum. Okay. So L is orbital angular momentum and S is spin angular momentum, and J is the total angular momentum for a system. Okay. So when an electron has got both orbital angular momentum and spin angular momentum, so we are going to calculate, or we are going to see another angular momentum which is called as resultant angular momentum. So this is called as resultant angular momentum. That is because due to the orbital angular momentum and spin angular momentum which has been possessed by an electron, we are going to observe a new angular momentum. So that is what is called as the total angular momentum, or it is also called resultant angular momentum, because this is formed, or this is observed because of L and S. Okay. So that is why the spin orbit coupling says that the total angular momentum for a system of electrons which is denoted by J is obtained by coupling the resultant spin and resultant total angular momentum. So that is why L plus L, L plus S minus 1, L plus S minus 2, and it goes on to L minus S. Okay. So this we are going to do in the vectorial combination. Okay. So you know that so the vectorial combination of different total spin angular momentum and resultant total angular momentum will give the values of J. Okay. So, the multiplicity is given by 2s plus 1. So, we are going to calculate the multiplicity for the number of such possible levels. Okay. So, these are the number of different possible levels which J can take. Okay. So, the number of possible levels is called as multiplicity, and the multiplicity is calculated by the formula 2s plus 1. Okay. So, now let us see when s is equals to 0, then the multiplicity is 2 into 0 minus 1, which will be equal to 1 or a singlet. So, j is equals to L. Okay. So, j is equals to L, and suppose if s is equals to 1 by 2, so then multiplicity is 2 into half plus 1, which will be equal to 2, or if we get 2, then we call it as doublet. Okay. So, in the same way, so if we get 3 here, then it is called as triplet. So, like this it goes on. Okay. So, this is how we are going to calculate the multiplicity of different states of electronic transition that can take place by a electron. Okay. So, spin orbit coupling is the total angular momentum for a system of electron, which is denoted by J, is obtained by coupling the resultant spin S and resultant total angular momentum as per the relation which has been given here. Okay. So, in the same way, suppose if S, that is the spin angular momentum, is equals to 1, then the multiplicity will be 3, or it is also called as triplet, and when S is equals to 3 by 2, then the multiplicity will take up the value of 4, and it is called as quartet. So, all these informations pertaining to the group or system of electrons is conveyed in a symbol, what is called as a term symbol. Okay. So, in Russell-Saunders coupling scheme, so term symbols are in the form of so 2s plus 1 Lj. Okay. So, in this structure we are going to write the term symbols. Okay. So, what are these term symbols? What and all informations we are going to get in this term symbol means, so here 2s plus 1 is the multiplicity, and where s represents the total spin angular momentum and L represents the total orbital angular momentum, and here the lower j which I have written here. So, this j refers to the total angular momentum. Okay. So, all the informations which we are going to get in a group or a system of electrons is conveyed in a single symbol. So, that is what is called as a term symbol. Okay. A state of an electron or the energy of the electron is denoted by certain symbol known as term symbol. Okay. So, this is how we are going to represent the term symbol. Okay. So, a term symbol is a symbol which is used to state which is used to say the state of an electron or the energy of the electron. State of the electron means in which subshell it has been present, in which orbital it has been present, and what sort of angular momentum, that is both orbital angular momentum and spin angular momentum, what type of angular momentum does the electron is going to possess. So, all these state of electron or the energy of the electron means whether it is in a ground state or whether the electron is in a excited state. So, all these informations can be obtained by studying the term symbol of a particular group or a system of electrons. Okay. So, this is what is known as spin orbit coupling. So, next so as I said further, so all these informations which we get by a term symbol, so that can be explained by considering Russell-Saunders coupling scheme. Okay. So, now let us consider Russell-Saunders coupling scheme for D2 ion, okay, or a D2 electron. So, it means, what does it mean? electron or a element which is having a D2 electron, for a D2 metal ion we will have the 2 electrons in the D subshell. Okay. So, now let us calculate the orbital angular momentum. So, here orbital angular momentum L is calculated by the vectorial combination of different orbital angular momentum. Okay. So, here if I calculate it in terms of the L is equals to L1 plus L2, and since here L is equals to 2, substitute the value here. So, L1 plus L2 is equals to 2 plus 2, which is equals to 4. Okay. So, in the same way, so next vectorial combination is L1 plus L2 minus 1. So, since L is equals to 2, substitute that value. So, I am going to get 4. Okay. So, L1 plus L2 is equals to 4, that I have already calculated here. So, for this substitute the value, and minus 1 which is equals to 3, and L1 plus L2 minus 2 is equals to 4 minus 2, which is equals to 2. In the same way, L1 plus L2 minus 3 which is equals to 1, and L1 plus L2 which is equals to 2 minus 2, that will become 0. Okay. So, therefore, so L can have values of 4, 3, 2 and 0. Okay. So, that means so if I write it in term letters, so it takes G, F, D, P and S. Okay. So, this I have to see it in table 2. So, from table 2, so see here. So, this is table 2. So, here if the value is 4, then it means that it is in G subshell, and if the value of L is 3, then it will take F, and if the value of L is 2, then it is D, and if the value of L is 1, then it is P, and if it is 0, it is S. Okay. So, that is how I am representing here. Okay. So, if the value of L is equals to 4, then it is G, 3 is equals to F, 2 is equals to D, 1 equals to P, 0 equals to S. Okay. So, this is how I am going to represent the values of orbital angular momentum. Therefore, corresponding term letters are G, F, D and S. Okay. So, to arrive multiplicity, now we know that multiplicity is given by 2s plus 1. Okay. So, now S is equals to S1 plus S2 which is equals to half plus half, which gives rise to 1, or S is equals to half minus half, which is equals to 0. So, these are the two possible ways or the two possible spins which we can observe. Suppose if the spin is in parallel orientation, then we will get 1, that is S1 plus S2, half plus half, which gives rise to 1, and if it is in anti-parallel, so then S is equals to half minus half, which gives rise to 0. Okay. So, further multiplicity is also calculated by the vectorial combination of different spin angular momentum. So, therefore, so 2 into 1 plus 1 which is equals to 3, and 2 into 0 plus 1 which is equals to 1. So, these are the two different possible multiplicity which we can assign for D2 electrons or a D2 metal ion. Okay. So, this is the example which we are explaining by taking the Russell-Saunders coupling scheme for D2 ions. Okay. So, for D2 metal ion we are studying here. So, for D2 metal ion we can have the term letters of G, F, D, P and S. In the same way, for D2 metal ion we can have the multiplicity of 3 and 1. Okay. Next is so the terms possible are 1G. Okay. So, what and all the terms possible? So, here consider the multiplicity also. So, we have to write the multiplicity in the upper of L value. Okay. So, upper of you see here. So, this is the term symbol. So, this is L. Okay. So, now we have calculated L. So, for G I am writing here. For G, that is if the L value is equals to 4, so then G is equals to 1. I am taking the spin multiplicity. So, the possible ways are, so 1G I can write, 3G I can write, and for F, this is for F, and this is for D, and this is for P, and this is for S. Okay. So, since in S only one electron can be occupied, so that is why so only one value will be observed here. So, among these terms, so only 3G, 3D, 1F and 1P violate Hund's rule, and therefore are not allowed. Okay. So, these term symbols, that is 3G, 3D, 1F and 1P, they will violate the Hund's rule and therefore are not allowed, and only 3F, 3P, 1D, 1G and 1S are allowed. Okay. So, therefore, the ground term for 3F has a multiplicity of 3F4, 3F3 and 3F2. Okay. So, to identify ground term among these, so Hund's rule is applied. So, here I am saying that so for this, so these are the different possible ways of writing the terms. Okay. So, the terms possible are so 1G, 3G, 1F, 3F, 1D, 3D, 3P, 1P and 1S. So, these are the different possible terms. Among these, so these 4 violate Hund's rule. Why they violate Hund's rule means, so here we have to see what does the Hund's rule says about. So, according to Hund's rule, the most stable state is that with maximum multiplicity. Okay. So, that is why, so we have to consider, so this one. So, here maximum multiplicity is so 3. So, 3 is the maximum multiplicity. So, for that reason, so 3F, 3G and this is possible, 3F and 3D is possible. Okay. So, that is for 3F or 3P, so the term symbol is possible. For groups of terms with the same multiplicity, that with the largest L value has its lowest energy. Okay. So, therefore, among 3P and 3F, the 3F has largest L value. Okay. So, F has got a largest L value. So, F means 3, okay, and P means 1. So, that is why, so 3 is large compared to P. Okay. So, F has got, so here see, F is having the L value of 3 and P is having the L value of 1. So, here F is larger compared to the P. So, therefore, so L value, and therefore, it is a ground term. So, due to spin orbit coupling, we have multiplicity state. So, they are arrived as follows. For F term, so L is equals to 3. Okay. So, therefore, the possible G values are L plus 1, L minus 1, that is 3 plus 1 is equals to 4, 3 and 3 minus 1 is equals to 2. Okay. So, therefore, the ground term for 3F has multiplicity of 3F, 3F3 and 3F2. Okay. So, by this we can understand that, so the 3F2 has lowest energy and 3F4 has highest energy. So, what does it mean? So, that means if you see this figure, so here we can clearly understand what has been discussed now. Okay. So, this is the D2 ion or a D2 electrons. Okay. So, D2 electron means in the D2 outermost electronic configuration, the 2 electrons which are present, so those 2 electrons might be in triplet terms and also they can arrange into the singlet terms. Okay. So, here the possible term symbol is according to the Hund's rule, what we have seen here. So, 3F, 3P is possible. So, that is what is shown here. So, 3F is possible and 3P is possible, and next is 1D, 1G and 1S is possible. So, 1G, 1D and 1S is possible. So, this is in singlet terms. Okay. So, these are the possible terms. So, the possible terms which will take according to the Hund's rule is, so in the triplet term we have 3F and 3P. So, here 3F and 3P are there, and for a singlet term 1G, 1D and 1S are there. So, this is according to the Hund's rule. Okay. So, in the same way, so the ground term will take different multiple states. Okay. So, what are those multiple states? So, by calculating the separation between the levels of J, So here we are going to calculate the separation between levels of J values as follows for the levels. Okay. So where J is equals to L minus 1, which is equals to 3 minus 1, and it will give 2, and J is equals to L, which is equals to 3, then we will have 3F3 value. Okay. So 3F3 is which is equals to 3 lambda. Okay. So these are the different possible microstates which we are going to see in the D2 metal ion. Okay. So this is the schematic representation of Russell-Saunders coupling. So this figure explains about the coupling scheme for D2 ions. So where we will see the two possible ways. So the two triplet terms, that is 3F and 3P, is represented here in the triplet term, and along with that, so the three singlet terms, that is 1G, 1D, 1S, is represented here. And further, so by the excitation which we will observe when a radiant energy is passed on to these electrons, so they will excite to the higher energy state, and this is calculated by the help of J values. Okay. So by the help of the J values, by applying the vectorial combination of orbital angular momentum and spin angular momentum. Okay. So the separation between 3F2 and 3F3 is 4 lambda, and the separation between the levels of 3F3 and 3F4 is 3 lambda. Okay. So that if you see it in the textbook by observing this figure and the explanations what I am giving to you, so if you go through the notes which has been given in the textbook, you will clearly understand what it is. Okay. So here 4 lambda and 3 lambda is called the spin orbit coupling constant. The energy separation between the levels produced by orbit, that is a spin orbit coupling, are expressed in terms of lambda. Okay. So what is lambda here is so the lambda is called the spin orbit coupling constant, and the energy separation between levels produced by spin orbit coupling. Okay. So on applying external magnetic field to the electron system, that is metal ion, which we have taken, that is a D2 metal ion, a further splitting of energy levels occur. Okay. So these are the further splittings of energy levels. Okay. So these further splitting of energy levels, and this effect is called as Zeeman effect. Okay. So how it is going to happen is, so this is the main excitation or the transition which we will observe in the D2 metal ion. You have to concentrate on this. Okay. So these are the main transition which is going to take place by the two electrons which is present in the D2 metal ion. So in terms of triplet terms and singlet terms. Okay. So on applying, so this is by calculating the orbital angular momentum and the spin angular momentum in terms of vectorial combination. So we are going to get different terms or the term symbols for these electrons, for the same electrons. Okay. So further, on applying external magnetic field to the electron system, a further splitting of energy level occurs, and this effect is called Zeeman effect. Then the value of J are split into 2J plus 1. Okay. So this is what is 2J plus 1, that is plus J to 0 to minus J. Okay. So the 2J plus 1 split status are equally spaced. Okay. So that is what is given here. So here the 2J plus 1 split status are equally spaced. So the separation between these states, so these states are or these states represents different energy levels. Okay. So the separation between these states is given by the term G beta H, where G is the Landis splitting factor and beta is the Bohr magneton and H is the applied magnetic field strength. Okay. This is how we are going to represent the schematic representation of Russell-Saunders coupling for a D2 metal ion. Okay. And the next topic is about the microstate. What is meant by microstate? So this is, see here, so these are the different microstates. Okay, so here 45 microstates have been observed. Okay, so the two electrons which are present in the D2 metal ion, when in the applied magnetic field, so they will take 45 microstates. That means so 45 different energy levels, so the two electrons which are present in D2 metal ion can take. Okay, so what is meant by microstate is so the different ways in which the electron can occupy the orbitals specified by the configuration are called microstates. Okay, I repeat, the different ways in which the electrons can occupy the orbitals specified by the configuration are called microstates. So these microstates differ from one another slightly in energy. Okay, so see here, so here if you can observe, so the microstates, so they differ from one another slightly in energy. The number of microstates may be calculated from the number of electrons and number of orbitals using the formula m is equals to 4l plus 2 factorial divided by q factorial into 4l plus 2 minus q factorial. Okay, so where q is the number of electrons in subshell with the azimuthal quantum number l. Okay, so here q is the number of electrons in subshell with the azimuthal quantum number l. So l is called as azimuthal quantum number. Okay, so L is equals to 1 for P subshell and 2 for D subshell, and it goes on like that. Okay. So for a D1 system, L is equals to 1. Okay. So for D1 system, so we can write the microstates as M is equals to 4 into 2 plus 2 factorial divided by 1 factorial into 4 into 2. So here 2 is missing. Okay, so here some mistake is there. So 4 into 2 plus 2 factorial divided by 1 factorial into 4 into 2 plus 2 minus 1 factorial, which gives rise to 10. Okay, so for D2 system, m is equals to 4 into 2 plus 2 factorial divided by 2 factorial into 4 into 2 plus 2 minus 2 factorial, which is equals to 45. In the same way for D3 configuration, so we will have 120. So the microstates is equals to 120. I hope you all know what is meant by factorial. Suppose here if it is 2 factorial means so 2 into 1 is equals to 4 factorial means 4 into 3 into 2 into 1. Okay, so 6 factorial means 6 into 5 into 4 into 3 into 2 into 1. So like that you can substitute the values and you can find out. Okay, so you check the values whether is it right or wrong. You check and see whether it is right or wrong. Okay, next is where n is equals to twice the number of the orbitals and r is the number of electrons. Okay, so where so in the microstates, in this so n factorial divided by r factorial into n minus r factorial. Okay, so this is the general representation. So this is the general representation. The number of microstates can also be calculated by using another formula. So that is this formula, another formula as given below. The number of microstates is equals to n divided by r. Okay, so n divided by r. So n means twice the number of the orbitals and r is the number of electrons. Okay, so this is another formula which is used to calculate the microstates. So for D7 configuration, n is equals to 2 into 5, which is equals to 10, and r is equals to 5. Okay, so substitute the values of n and r in the above equation. So you will get 120. So that is what for a D7 configuration we will have
120 microstates. Okay, and this is the table which gives us the electronic arrangement. So if the electronic arrangement is in this way, p1 p2 p3 p4, and how many number of microstates we are going to get. And suppose if the electronic arrangement is in D form, so that is a D1 D2 D3 D4 system. So this is for P system and this is for D system. So the number of microstates, so this is the calculated number of microstates for different electronic arrangements in P subshell and D subshell. Okay, so I am going to stop it here. So in my next class we will see what is meant by spectroscopic ground state for DN system. Okay, so thank you dear students.